transformer conductors are sized based on the overcurrent protective device rating. In the given example, with a 125 amps overcurrent protective device on the primary side and a 225 amps overcurrent protective device on the secondary side, the primary and secondary conductors of the transformer would be sized to carry 125 amps and 225 amps respectively, even though the transformer has a capacity of 75 kilovolt amps, with a primary voltage of 480 volts and a secondary voltage of 208/120 volts. Let's delve deeper into the principles behind the sizing methodology. The National Electrical Code, or NEC, provides specific guidelines for the protection of electrical systems, including transformers. These guidelines are put in place to ensure safety and prevent damage due to overloads or short circuits. One of the fundamental concepts in electrical engineering is that conductors must be protected against overcurrents. Overcurrent can result from several scenarios, including short circuits, ground faults, or excessive loads in the circuit. When an overcurrent occurs, the conductor can overheat, potentially leading to insulation breakdown, fire hazards, and equipment damage. To prevent these hazards, overcurrent protective devices such as circuit breakers and fuses are installed in the circuit. These devices are designed to interrupt the flow of current when it exceeds a predetermined level, thereby protecting the conductors and other equipment in the circuit. Now let's focus on the specific case of transformer conductor sizing. Transformers are essential components in electrical power distribution systems used to step up or step down voltage levels. When sizing conductors for a transformer, it is important to consider both the transformer's rated capacity and the overcurrent protection requirements. The NEC specifies that transformer primary conductors must be protected by an overcurrent device rated at not more than 125% of the transformer's rated primary current, unless certain conditions are met that allow for higher overcurrent protection. This rule ensures that the primary conductors are adequately protected against overcurrents originating on the primary side of the transformer. Similarly, the NEC provides guidelines for protecting transformer secondary conductors. In general, secondary conductors must be protected by an overcurrent device rated at not more than 125% of the transformer's rated secondary current. However, there are exceptions to this rule, particularly when the secondary conductors supply multiple loads or when the transformer is used in specific applications. In such cases, the overcurrent protection may be sized differently based on the specific load characteristics and the overall system design. To illustrate the concept, let's consider a scenario with a 75 kV amps transformer with a primary voltage of 480 volts and a secondary voltage of 208/120 volts. According to the nameplate data, the transformer has a rated primary current of approximately 90 amps and a rated secondary current of approximately 208 amps. However, the actual overcurrent protection devices installed on the primary and secondary sides may be rated higher than these values, depending on the specific installation requirements. For example, the primary overcurrent protection device may be rated at 125 amps, while the secondary overcurrent protection device may be rated at 225 amps. In this case, the primary conductors must be sized to carry at least 125 amps, and the secondary conductors must be sized to carry at least 225 amps, regardless of the transformer's rated current. It's important to note that the conductor ampacity must be selected based on the termination temperature ratings of the connected equipment, as specified in NEC Table 310.16. This table provides ampacity values for various conductor sizes and insulation types, considering the ambient temperature and the number of current-carrying conductors in a raceway or cable. In addition to the overcurrent protection requirements, other factors must be considered when sizing transformer conductors. These factors include voltage drop, conductor insulation type, ambient temperature, and the presence of harmonics in the system. Voltage drop refers to the reduction in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment malfunction and reduced performance. Therefore, Conductors must be sized to minimize voltage drop within acceptable limits, typically 3% for branch circuits and 5% for feeders. Conductor insulation type affects the conductor's ability to withstand heat and environmental conditions. Different insulation types have different temperature ratings and are suitable for various applications. The appropriate insulation type must be selected based on the ambient temperature, the presence of moisture or chemicals, and other environmental factors. Ambient temperature refers to the temperature of the surrounding environment. High ambient temperatures can reduce the ampacity of conductors, as the conductors tend to overheat more easily. Therefore, conductor ampacity must be derated based on the ambient temperature, as specified in NEC Table 310.16. Harmonics are distortions in the sinusoidal waveform of alternating current. Harmonics can cause overheating of conductors and equipment, as well as other problems. In systems with significant harmonic content, conductors must be sized to accommodate the additional heating caused by the harmonics. In summary, transformer conductor sizing is a critical aspect of electrical system design. Conductors must be sized to carry the load current and to provide adequate overcurrent protection. The overcurrent protection device rating typically dictates the minimum conductor size. In addition, other factors such as voltage drop, conductor insulation type, ambient temperature, and harmonics must be considered to ensure safe and reliable operation of the electrical system. Now let's explore the nuances of the NEC requirements related to transformer protection and conductor sizing. Article 450 of the NEC covers transformers in detail, outlining the specific requirements for overcurrent protection, grounding, and other aspects of transformer installation. Section 450.3 of the NEC specifically addresses the overcurrent protection requirements for transformers. This section provides detailed rules for sizing overcurrent devices for both the primary and secondary sides of transformers, taking into account the transformer's voltage, current, and impedance. As mentioned earlier, the general rule is that transformer primary conductors must be protected by an overcurrent device rated at not more than 125% of the transformer's rated primary current. However, there are exceptions to this rule for transformers with impedance of not more than 6%. In such cases, the overcurrent device may be rated at not more than 250% of the transformer's rated primary current. This allowance is based on the fact that transformers with high impedance tend to limit the fault current to a greater extent, reducing the risk of damage to the transformer and conductors. Similarly, the NEC provides exceptions to the general rule for secondary overcurrent protection. For example, if the secondary conductors are protected by an overcurrent device on the primary side of the transformer, and the primary overcurrent device is sized to protect the secondary conductors, then a separate overcurrent device on the secondary side may not be required. This exception is often used in installations where the transformer feeds a single load, such as a motor or a heating element. In addition to the overcurrent protection requirements, the NEC also specifies requirements for grounding transformers. Grounding is essential for safety, as it provides a low impedance path for fault currents to flow back to the source, tripping the overcurrent device and preventing electric shock hazards. Section 450.10 of the NEC outlines the grounding requirements for transformers, including the size and type of grounding conductors, as well as the methods for connecting the grounding conductors to the transformer and the built-in grounding system. Another important consideration in transformer conductor sizing is the coordination of overcurrent devices. Overcurrent coordination refers to the selection and arrangement of overcurrent devices in a manner that ensures that the device closest to the fault will trip first, minimizing the extent of the outage and preventing unnecessary tripping of upstream devices. To achieve proper overcurrent coordination, it is necessary to perform a coordination study, which involves analyzing the fault current levels at various points in the system and selecting overcurrent devices with appropriate time current characteristics. The time current characteristic of an overcurrent device describes the relationship between the current flowing through the device and the time it takes for the device to trip. By selecting overcurrent devices with appropriate time current characteristics, it is possible to ensure that the downstream device will trip before the upstream device in the event of a fault. In addition to the NEC requirements, other standards and guidelines may apply to transformer conductor sizing depending on the specific application and location. For example, the Institute of Electrical and Electronics Engineers, or IEE, publishes various standards related to transformer design, testing, and installation. These standards provide guidance on topics such as transformer insulation, temperature rise, and short-circuit withstand capability. Local codes and regulations may also impose additional requirements on transformer conductor sizing. It is important to consult with local authorities and qualified professionals to ensure compliance with all applicable codes and regulations. To summarize, transformer conductor sizing is a complex process that requires careful consideration of various factors, including overcurrent protection, voltage drop, conductor insulation, ambient temperature, harmonics, and applicable codes and standards. By following the guidelines outlined in the NEC and other relevant standards, it is possible to size transformer conductors in a manner that ensures safe, reliable, and code-compliant operation of the electrical system. When working with electrical systems, always prioritize safety. Ensure that you are qualified and knowledgeable to perform the work. If you are unsure about any aspect of the installation, consult with a licensed electrician or a qualified electrical engineer. Remember, electricity can be dangerous, and it is essential to take all necessary precautions to prevent accidents and injuries. Always to energize the circuit before working on any electrical equipment. Use appropriate personal protective equipment such as insulated gloves and safety glasses. Follow all applicable safety procedures and guidelines. By adhering to these safety practices, you can help ensure a safe and productive work environment. Proper conductor sizing protects the electrical system, the equipment connected to it, and most importantly, people.